and we're going.
Okay, so at the end of last lecture, what we got up to was pointing out that there are vector value function spaces that are not just the Cartesian product of scalar value function spaces. And so we will start from there and probably repeat ourselves a little bit to ramp up. And then the guts of today's lecture is going to be about why that involves you doing something slightly more complicated when you do the change of coordinates to local coordinates, and what the properties of that change of coordinates are, and its slightly counterintuitive properties. So, if we remember then, the easy way of getting a vector value function space was we said, okay, we've got a scalar value function space, and that scalar value function space has, we can just for the moment talk about local basis functions. So that's phi I or x, and it's helpful to keep P1 in mind because it's the easiest one to think about. So if we were in P1, then the scalar value basis functions, there would be 3 of them. And the easy way of getting a vector valued space is to simply multiply this by E alpha, where E alpha is one of the basis functions of the normal Cartesian space. So it's the one of these 3, right? So that's the x basis function, that's the y basis function, and that's the z basis function. And these things behave rather simply because what we're really doing is we're storing 3 separate scalar fields, and so the transformation rules are very, very easy. In particular, if I remember that somewhere out in real space I've got an actual triangle, and I have a mapping which, in order to not confuse myself with the paper today, I will be calling F for the purposes of today's lecture, then F maps points x to points little x, but we don't have to do anything to the vector values. So the vector values over here are with respect to the traditional basis, and that basis does not change for whatever shape this element is. It doesn't matter which way up the element is, it doesn't matter whether the element is bendy or not bendy, it doesn't matter how squished it is, the vectors are the same. And so that is great because it means that when we change coordinates from one space to the other, we don't have to do anything to our vector values. So that's different to the transformation that we already knew we had to apply to derivatives. Right? So already in a previous lecture, we learnt that if we have the gradient over here, which we might call gradient big X, and the gradient over here, which we might call gradient little x, then it's not sufficient to simply substitute one of these for one of these, because what this one means is the xi, and we ask ourselves, is that equal to this? And the answer is, of course, no, but it would be equal if we put the appropriate change of coordinates in. So the appropriate change of coordinates is the xi d little xj. And we call that the inverse Jacobian. So the Jacobian would be the small x d big X, right? That's the gradient of this function. So this function gives you small x's given big x's. So its Jacobian will be the other way up. And so this we call J inverse. And so you have to transform the gradient with this to get from here to here. And the reason that that's happening is if you ask yourselves, what did this gradient operator do? It took the derivative in the directions of the local coordinates over here. And the local coordinates don't point in the same direction as the global coordinates. Right? So if I actually draw this, I've actually drawn a rather equilateral looking reference triangle here. How about I actually draw the reference triangle that is used in Phoenix and Phi, which is this one. And so I have, in this case, two local coordinates. One of them points this way, and one of them points this way. So if I arbitrarily decide that that is the mapping of the three vertices as I go out to real space, that means that as I go from here to here, this vector direction here has to transform to this vector direction, and this vector direction has to transform to this vector direction. And that's in fact what the Jacobian here is doing. So that's why a few lectures ago we went through this whole palaver of having to insert Jacobians onto all our derivatives. Okay, so the reason I'm resurrecting that whole sorry story is because once we start looking at slightly more interesting vector valued spaces, we've kind of got to do the same thing. So what we're going to do is motivate a little bit the use of vector valued basis functions by the operators we might want to use. So there's a much more rigorous version of what I'm going to do, and it's tied up with all the exterior calculus stuff. And as I keep telling you, Colin's been running a rather wonderful informal course in that direction. But we can motivate it using the same operations, but using our language. So suppose I've got my mesh, and I've got a piecewise continuous P1 space on this mesh. And I ask myself, what properties does the gradient of this have? And in particular, I'm interested in the continuity of the gradient as I go from one triangle to the next. Because if you remember before, we've already learned that in order to take a weak gradient, you need a continuous space. And what actually happens in one dimension as we take the gradients of our piecewise continuous space is we get a piecewise discontinuous space because the gradient jumps as we go over the edges of the elements. So what happens in more dimensions as we take a gradient? Well, here it's useful to have a little prop, and fortunately there's a nice folded piece of paper sitting on the ground here. So here's my nice two-dimensional, continuous but not differentiable function, right? So it's whatever smooth polynomial I like here, it's another whatever smooth polynomial I like here, and it's got a ridge on it. And now I ask myself what the gradient vectors of this are going to look like. Well, if I look at the gradient vectors in the direction normal to the edge, then pretty clearly, as I go over here, they're going to jump. They're going to change direction suddenly. So I expect there to be a discontinuity in the gradient as I look in the normal direction. But what about the tangent direction? Well, in the tangent direction, actually the gradient has to stay continuous as I go over. There's no jump. And so if you take, in the natural way, the gradient of C0 functions, you end up with functions which have discontinuous normal components and continuous tangent components. And conversely, if you took the equivalent of the curl operator, if you took the skew gradient, then you'd get the opposite. You'd get that the skew gradient, the gradient rotated through 90 degrees, is continuous in this direction and discontinuous in this direction. And so that gets us an important class, the two important classes of spaces. We can have function spaces where we have normal continuity and tangent discontinuity, and function spaces where we have tangent discontinuity and normal continuity. And they turn out to be really important spaces because they're still somewhat weak differentiable. Right? I can't then take the weak gradient operator. So there is a gradient operator for vector value functions. And in fact, we've seen it, right? It gets you a matrix, and that's exactly what the Jacobian is. Right? The Jacobian is the gradient of the coordinate. The coordinate's a vector value function. So there is a gradient operator there, and in accordance with our rules for taking weak derivatives, we couldn't take a weak gradient in a space that didn't have complete continuity along the edges, because you need continuity in all the components. But we can take other sorts of gradient, other sorts of derivative. So let's, for starters, imagine that we have a space which has continuous normals. And the easiest one of those is the space where the degrees of freedom are the normal flux through each face. So this space is called the Rabi-Artoma space. It's the lowest order Rabi-Artoma space. In most of the literature, this is called RT0. In some of the literature, and in particular anything written by people from the Phoenix crowd, this is called RT1. So the disagreement is about whether you number the space by the largest polynomial space that it spans, or the smallest polynomial space needed to contain the space. Because this thing is linear, but not all the linears. So it's the space of linear functions which are constrained to have constant normal components. And then the normal components are tied up between them. So the normal components are continuous, but the tangent component at this point, so this basis function has no tangent component on this edge. But these basis functions do. They don't vanish down here. And so the tangent component on this side is given completely by these values, and the tangent component on this side is given completely by these values. So the tangent components at this point have nothing to do with each other. Could be completely discontinuous. But that's okay, because if we remember what we need in order to do a weak derivative, basically it's equivalent to being able to integrate by parts when the other function is very smooth. So if I take not the gradient, but the divergence of my function, so this function is going to live in this space, and I multiply this by some test function which I'm going to make infinitely well behaved, so it's a completely smooth function, and I integrate this by parts, so that is equal to minus the integral of u dot grad phi dx, and so that's fine because that's infinitely differentiable, so that's allowed, plus the boundary integral of u dot n times phi dx. And so what we discovered previously is that in order for the weak derivative to actually work out globally, these need to cancel from both sides. So they cancel as you go over the element edges if u dot n seen from this element is minus u dot n seen from this element. And that's equivalent to them being, to u being continuous, u dot n being continuous. But notice it said nothing about the tangent component. And something very, very similar falls out if we had the other space, so the space which only has a tangent component on each side, and I took curl, and integrated curl by parts, then I'd get a tangent component here, and the tangent component would need to cancel. So, okay, so that's why we care about these spaces, because they're the natural spaces to be the derivatives of continuous spaces, and actually it continues through. So if you ask yourself which space is the divergence of one of these in, well, it's in a completely discontinuous space. So those of you who've seen the traditional set of elements for Rabi-Artomas, if you use this for velocity, then you'd use P0 dg for the pressure. And that's because the pressure is related to the velocity by the divergence operator. And so it's, in some sense, a natural space. And you can do lots of beautiful maths where you prove that your numerical scheme has wonderful properties by obeying those rules. And if you write them down in the exterior calculus form, you can do that in about half a page of A4 paper normally. So that's the motivation. That's why we care about these things. So now, having decided that we care about these function spaces and we want to have them, So we then have to start worrying about what happens when we change coordinates back to the reference triangle. So the problem we're going to have here is that the reference triangle looks like this. So these are going to, that's the global basis functions, like that. So the reference triangle is going to have basis functions, and they had better somehow look a bit like this, because we need the local basis functions to have the right continuity behavior such that when we do a jump integral internally it cancels, for example. Those are like the basic rules we need. So this is now a different situation from the situation we had a few minutes ago. It's not the situation where as we move one of these components to here, it just maps to itself. Right? Now this needs to rotate and possibly rescale according to the size of these things. So we're actually in the situation which is much more analogous to what happened when we transform the derivatives. Right? The vector value quantities have to transform with the transform rather than just staying invariant under the transform. So it turns out that there are transformations for doing this, and they're called the Piola Transforms. And now I'm going to take up Marie's paper, because if I just write them down, I'm going to get this wrong. So what you want to be able to do is map so what we have is somewhere we have a local vector value basis function, and back in this space we have a global basis function. And so what I have to do to my basis function to get from one to the other is I have to say that this is equal, so in H div, so by H div we mean this space with the continuous normals. The reason we call it H div is because this is the space in which divergence works. It's a space where you can take a weak divergence of the functions. The other space with continuous tangents is called H curl, because it's a space where you can take a weak curl. And then the relationship between these is 1 over the determinant of J times J. That's called the contravariance Piola transform. And if I'm in H curl, then the transformation would go the other way around. So I would get so that's the transpose of the inverse of J. So this is actually how the derivative transforms. Right, that's a familiar expression, and this is not. And so in order to see why these are the correct transformations to use, what we want to study is what these transformations do to the normal and tangent components of these cells, right? Because that's what we're interested in. We're interested in getting the transforms right such that we keep continuous normal components or continuous tangent components according to which one of the transforms we're doing. It's the important property. And so the best way to do this is to actually apply the Piola transform to the vectors which define the edges and the normals. So what we can do is, let's just take ourselves back to one triangle over here. so if we start with the reference triangle, so the reference triangle is now going to have vertices x and I, so x0, 1, 2 or x1, 2, 3, depending on whether you like to count in Fortran or C. And it's going to then also have 3 edges, and the edges are kind of be called I. And the normal convention is edge I is the edge opposite vertex I. That uniquely defines them. For the current purposes, we're not going to care what the actual numberings are, because we're just going to do this for an abstract edge. And if you've done that, then so edge I is a vector, right? So edge I is going to be xa and you can get the A's and B's the right way round to make your signs come out. That's not important for us currently. It's not a particularly relevant situation. And so I can just rescale that to get the unit tangent on this edge. Right, so the unit tangent is just a vector that points in this direction which has length 1, and so that just naturally means that the unit tangent on edge I is equal to the vector defining that edge divided by the length of that vector. And let me remove some debris here, rather than writing over it myself, because that will just confuse matters. So because we're currently running through all this in 2 dimensions, which makes our life easy, we can also at the same time pick up a set of unit normals that are going to work with us. And the way we get the unit normals is by rotating the unit tangents. And because we're in nice 2-dimensional space, that means we just have a 2-dimensional matrix. So the normal is going to be equal to a rotation matrix times Ti. And the rotation matrix is very, very simple. Obviously it's a rotation matrix, so it's that was easy, right? And that gets you the tangent ones. And so now we're going to assume that we have this function here, which is mapping us to there, and we're going to wimp out and make our life simple for the moment, because they get very complicated if you don't, and assume that that mapping is affine. So for the purposes of the amount of algebra we're about to dump on the board, we will assume that this thing is equal to Jacobian times x plus offset. So just makes this whole process an awful lot neater. And obviously, it's actually sufficient, by the way, if you want to get into defining this, knowing that this is affine, you can just define it by the fact that it maps the vertices to the right spots. If you just work out how many degrees of freedom there are in the map, then that's sufficient to work to define it. And in fact, that's what you do for real, right? Because what you actually do is you define this map using the basis functions for the P1 space here. And that's exactly equivalent to just knowing what the vertices are. So that's great. Oops, I'm zooming like crazy here. And so what that does for us is it shows us what happens to the edges under this mapping. Right? So it means that if I have an edge in physical space, that's going to be xa minus xb, and that's going to be right? And so now, in order to get the normals, we need to do a little bit of matrix algebra. So in order to get the normals out of this, we need a couple of identities. And so the first one is that 1 over the determinant of the Jacobian Rj Rt is equal to, right, so I'm not going to expand that out now, but that, if you expand it out, is just a consequence of the normal formula for writing out the inverse. Right, so you can write out the inverse in terms of the Jacobian. And so if you just write out what the inverse is, then that falls out. It's just a simple matrix identity, and from that you know that the rotation applied to J is equal to det J times J minus T times R. So RTR, so R and RT are each other's inverses. So that was just a rearrangement. I should move that to here and effectively move that to here. So minus T is it transposes the inverse. You can write it as minus 1 brackets T if you want. It's just a notational convenience. So the reason that we wanted those expressions is that we now want to know how the normals go. So the normals are, remember that in the definition of the normal, what you do is you rescale the edge and then rotate it. So this was actually the transformation of the edge, not the tangent. And so if we want to rescale, if we want to transform the normals, what we're actually transforming is, well, in terms of the things we already know, is, I'm going to go over here, that doesn't likely, is edge times normal, right? That's just a direct consequence of the fact that we define normals as being unit long. Otherwise, this turns out to be the transformation of the normal, which is of the same length as the edge, which is just inconvenient. And so that is equal to the rotated edge. And if that's equal to the rotated edge, that's equal to the rotation of the Jacobian applied to the reference edge. That's just what we wrote down. And if that's true, then we can use this identity that we just wrote down here. So there's an Rj, which is an Rj over there, so we can just substitute that straight into there. So that gets us, I really do need to stop flicking to the wrong page. So that gets us det J times J minus T times the rotated edge. And from the definition of the normal, that is just equal to det J times J minus T times the length of the reference edge times the normal. Or in other words, the normal scaled by the real edge length is the contravariant Piola transform inverse of the of where we started. So that's good news. So now what we want to do is, now that we know how to transform the normals and the edges, that wasn't actually what we cared about, right? What we cared about was what happens to the normal and tangent components of a function defined on the triangle. Right, so the reason why we've gone through all of that mess is because we can write then down normal components and tangent components by taking the dot product of functions with normal and edge and then hit them by the transforms, and we now know the rules for doing that. So we'll keep those rules up there and start over here. So I want to know what happens to this guy. Right, I want to know what happens to the normal component of some function that I have in the space. And actually that's what I know about. Right, that's just a convenience as I put this through. And so what is this? Well, if we're in HDiv, we've defined our transform, right? We've defined how to transform this guy using the contravariant Piola transform, and we know how this guy transforms. So that's going to be equal to, so this guy stays here, and that's going to be J over get J. I'm just going to swap to the blue pen because this marker is on the way out and I'm concerned about how readable this is going to be. Times the local basis function, right? So that's this bit here under the contravariant Piola transform. And then what does n become? So, back to my page again. So he becomes, so if I just take this formula here and divide through by the scale of E, so that's on this side, that gets me norm of J inverse. Let's not forget that there's a dot product in there, that's really important. Norm of J inverse norm of E over norm of little e, because I need to rescale to get the n, times the local normal. So
I'm a bit confused going back to a few steps where you have J inverse T and J inverse. So in the middle column, you've got what looks.
Sorry, that's a minus T. Is that what you're confused about? Yeah.
It's -1 over there.
That's just lost, right? That's just lost in translation from that line to that line. Okay. So now what does this do? So, well, all the scalars just cancel out straight away, right? So that guy cancels with that guy cancels with that guy. And now the fact this is a dot product is important, right? Because that transposes the left operator. So that's J transpose hitting J minus transpose. So that guy cancels with that guy. And so this turns out to be so I start off with the normal components in physical space of my function, and I end up with the normal component in reference space of my function. And what's gone on here is they're scaled by the lengths of the real edge and the local edge. So the Piola transform, in essence, gets the rotation right, and then you have to get the scaling right. And the scaling is given by the relative sizes. And there is a trap here, right? So there's a reason why we're tracking around the edge length here, because you might think, well, it's just the reference space, so I can just define it away. And you can just define it away depending on how you want to define your local coordinates and do your local triangle. But using the local triangle that we normally use, that's not the same on all sides. Because it's a normal right-angled triangle, it's got two sides of length 1 and one side of length root 2. So that is not quite trivial. What you can do though to make that go away is you can decide that the degree of freedom you will store will be the degree of freedom stored by scaled by edges, and that makes that one go away. So that was good news. We can do the same thing again by looking at what the covariant Piola transform does to tangent components. And we'll just do that as the last thing before the break, and then we'll come back and examine the consequences of all this after we've had a short break. So let's do the covariant Piola transform. So what we had now was the scaled tangent component. Right, so this is now the physical tangent, physical edge length, physical basis function, global, if you prefer to physical, same thing. So what's that going to be? So that's going to be the length of edge times the transform of this guy, which is j minus t by x, dotted with the transform of this guy, which we worked out a little while ago, and so that is j edge over edge times big T. If anyone is following along in the paper, there's a typo in the paper at this point. The paper is missing the big T there. And what happens? The same magic, right? So this guy cancels with this guy. This guy gets transposed by the fact this is on the left-hand side of the dot product, so that's now J inverse in J, so they cancel. And I get that this is equal to the edge length scale of, keep going so you can get that right, that's hitting the local tangent. So all we did was use the same formula, right? H is equal to JH. So that was good news. So they work. So that's the algebraic version, and we're going to take a break now. When we come back after the break, we'll look at this geometrically and understand what the consequences of that are.